This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. Today we'll be delving into a research paper detailing the StarWhisper telescope, SWT system, an agent-based observation assistant designed to streamline astronomical observation processes. The paper focuses on automating tasks traditionally handled manually by astronomers. What are the key challenges in astronomical observation that SWT aims to address?
The primary challenges lie in the labor-intensive nature of observation planning and data processing. Generating observation lists for multiple telescopes across various sites requires careful consideration of factors like sky visibility, object selection from extensive catalogs, and telescope capabilities. Similarly, analyzing the massive amounts of raw image data to identify transient events like supernovae is extremely time-consuming. SWT aims to automate these phases, freeing up astronomers for higher-level tasks.
The paper mentions the Nearby Galaxy Supernovae Survey (NGSS) project as the application context for SWT. Can you elaborate on NGSS and its relevance to the development of this system?
NGSS involves 8 telescopes spread across 3 observation sites, aiming to detect supernovae in nearby galaxies. This distributed nature and the sheer volume of data generated make it an ideal testbed for an automated system like SWT. The scale of NGSS highlights the need for efficient tools to manage the observation workflow.
The core of SWT is its use of large language models, LLMs, and agent-based workflows. How does this approach differ from traditional astronomical observation control systems?
Traditional systems often rely on complex, pre-programmed workflows and specialized interfaces. SWT leverages LLMs to enable natural language interaction, making the system more accessible to a wider range of users, including amateur astronomers. The agent-based architecture allows for flexible adaptation to different observation strategies and real-time adjustments based on various factors.
The paper discusses several LLMs and agent workflow platforms. What were the key considerations in selecting the specific technologies used in SWT?
The choice of LLMs was influenced by factors like performance, cost-effectiveness, and availability within China. The paper details a comparison of several models, ultimately selecting Qwen 2.5 Instruct 14B for its strong instruction following capabilities and cost efficiency. The selection of agent workflow platforms involved balancing ease of use, local deployment capabilities, and the ability to integrate with existing tools and APIs.
The SWT system is modular, encompassing observation planning, control, data processing, and agent reporting. Can you walk us through the functionality of each module?
The observation planning module uses LLMs and workflows to generate customized observation lists for each telescope and site, considering factors like object visibility and telescope capabilities. The observation control module interfaces with the NINA software to automate the observation process. The data pipeline module processes the observed data in real time, identifying potential transients. Finally, the agent reporting module provides feedback to the observer, including weather updates and transient alerts.
The paper highlights the integration of auxiliary tools like weather reporting and transient name server (TNS) searches. How do these tools enhance the overall functionality of SWT?
These tools provide crucial contextual information to the system and the observer. The weather reporting module allows for real-time adjustments to the observation schedule based on weather conditions. The TNS search agent helps identify previously known transient events, preventing redundant observations and potentially highlighting interesting targets.
The paper mentions a previous experiment with the mini-CT telescope. What insights did this experiment provide for the development of SWT?
The mini-CT experiment served as a proof of concept, demonstrating the feasibility of using agent-based workflows for telescope control. It provided valuable experience in developing communication protocols and integrating LLMs with existing telescope control systems. The lessons learned from this smaller-scale experiment were crucial in designing and implementing the more complex SWT system.
The paper discusses the concept of an embodied telescope. How does this concept relate to the future development of SWT and the CTN project?
The embodied telescope represents the ultimate goal: a fully autonomous system capable of making real-time decisions and adapting to unforeseen circumstances. SWT, as it currently stands, is a significant step towards this goal. The CTN project, with its large array of telescopes, provides the ideal platform for realizing the embodied telescope vision. This would involve enhancing real-time analysis, exception monitoring, and new object injection capabilities.
The paper outlines several future improvements for SWT, including enhancements to data processing, agent workflows, and edge computing capabilities. What are the key challenges in realizing these improvements?
Key challenges include developing more robust LLMs capable of handling complex decision-making tasks, improving the accuracy of real-time data analysis, and addressing the computational and communication constraints of deploying the system in remote locations. Edge computing will be crucial for managing the data flow and control signals efficiently in a distributed network of telescopes.
The paper also discusses the importance of observation monitoring for unattended observatories. What measures are being taken to ensure the reliable operation of SWT in such environments?
A dedicated observation monitoring module is being developed to monitor various aspects of the telescope's operation, including its physical state and electronic signals. This module will detect anomalies, attempt automated fixes for minor issues, and alert the observer for more serious problems. The system will also leverage a knowledge graph built from operational data and the observer's handbook to provide automated troubleshooting guidance.
The paper concludes with a discussion of the potential for SWT to lower the barrier to entry for amateur astronomers. How does this aspect contribute to the broader goals of the NGSS and SETIAN projects?
By making astronomical observation more accessible through natural language interaction and automated workflows, SWT can significantly broaden participation in these projects. This increased involvement can lead to more discoveries, more efficient use of telescope resources, and a greater understanding of the universe.
The paper emphasizes the importance of comparing LLM-generated observation control systems with those developed by human engineers. What are the potential benefits of such a comparison?
This comparison would provide valuable data for training LLMs, highlighting common errors and improving their ability to generate reliable and safe control commands. It would also help identify areas where LLMs excel and where human expertise remains essential. This iterative process of comparison and refinement is crucial for building trust and ensuring the safety of expensive astronomical equipment.
Finally, what are the most significant long-term implications of the SWT system and its potential evolution into a fully embodied telescope?
The long-term implications are profound. A fully embodied telescope could revolutionize astronomical observation, enabling continuous, autonomous monitoring of the sky and leading to a dramatic increase in the rate of discovery. This could accelerate our understanding of transient events, improve our ability to respond to time-critical observations, and ultimately reshape our understanding of the universe. The accessibility provided by natural language interfaces will also democratize access to astronomical research.
Thank you for this insightful discussion.